Okay, let's start. Good morning, good afternoon, and good evening. Welcome to the week 3 for S2S monthly webinar. Today's session features only one distinguished speaker, Dr. Jaeyeon Lee from NOAA GFDL. Unfortunately, Dr. Angel Minus from Barcelona Computing Center, he has a family emergency, so he couldn't make it today. So for further details and resources, kindly refer to the week 3 for website provided in the chat box. In addition, we encourage active participation through the discussion document available in the chat during and even after the webinar. The speaker will contribute to addressing any questions or comments you may have. Okay, looking ahead, our next webinar is scheduled for June 3rd at 2 p.m. Eastern Daylight Time. Okay, we can start with Dr. Jaeyeon Lee. His presentation is entitled with Size-Dependent Sensitivity of Northern Hemisphere Extratropical Cyclones to Atmosphere Resolution Change in the GFDL Sphere Model. Go ahead.
Good afternoon, everyone. I'm Jaeyeon Lee, postdoc in GFDL and Princeton AOS program. It is a great honor to sharing my research work here today. Today, I'm going to talk about wintertime mid-latitude cyclones, size-dependent sensitivity to atmosphere resolution change. This work has been conducted with Dr. Xiaosong Yang, Professor Edmund Chang, and Dr. Hiroyuki Murakami. I want to extend my gratitude to them. In the mid-latitude region, not only is there a vertical temperature gradient, but also a strong horizontal temperature gradient exists. To mitigate this instability, turbulent eddies are generated, which subsequently lead to the development of extratropical cyclones. These developed cyclones can trigger weather phenomena such as storm surges or cold breaks. However, predominantly, they generate rainfall in mid-latitude, presenting a comma-shaped cloud pattern in this satellite image. Rainfall induced by this extratropical cyclone is known to account for approximately 85% of the total winter precipitation. It underscores the importance of accurate prediction for extratropical cyclones. The figure illustrates the contribution of extratropical cyclones to winter precipitation in Northern Hemisphere. Observations indicate that extratropical cyclones account for up to 85% of rainfall in the Northern Hemisphere. And this large contribution of extratropical cyclones in observation is also evident in global climate models. This implies how crucial it is to accurately simulate extratropical cyclones for wintertime precipitation prediction. However, GCMs struggle to accurately simulate the characteristics of extratropical cyclones. The left figure depicts the cyclone frequency distribution simulated by RealSys data and CMIP6 models, and right figure illustrates the difference between them. CMIP6 models generally capture the location of major storm track well, but they often fail to simulate the detailed position and quantify the cyclone frequency. Some studies argue that these issues in GCMs stem from their two coarse resolutions. The figure shows the bias in cyclone frequency for high resolution CMIP and low resolution CMIP. High resolution CMIP exhibits better representation for exotropical cyclone frequency in some regions compared to low-resolution CIMI. However, high-resolution CIMI models still show larger cyclone frequency bias in certain areas compared to low-resolution models. This locally different sensitivity of exotropical cyclone frequency bias indicates our partial understanding of how increasing resolution affects the simulation of exotropical cyclones in GCMs. Additionally, CIMI models 100 kilometer atmosphere resolution is still too coarse for simulating cyclones. Therefore, this study aims to utilize the GFDR sphere models with a final resolution from 100 kilometer to 25 kilometer for investigating how the characteristics of the exotropical cyclone change with increasing atmosphere resolution. We also seek to identify the characteristics of extratropical cyclones that are sensitive to resolution change. Sphere models is used in this study. This model is a newly developed fully coupled GCM in GFDL. Sphere models are configured at atmosphere and land components with 3 different horizontal resolutions and 1 degree horizontal resolution ocean and sea ice components. It allows us to examine cyclone sensitivity to atmosphere resolution change. In this study, we use these 3 sphere models, sphere low, sphere medium, and sphere high, with 10 ensemble members each. This study utilized the track algorithm to detect and track cyclones in the cerebral pressure field. Cyclone tracking studies use spectral filter to exclude small-scale noise at the surface. Most previous CIMIP studies used T42 due to their coarse resolution. However, sphere model allows us to use higher spectral truncation resolution with which enable to detect more realistic cyclone shape and detect more cyclones. The cyclone cerebral pressure field is spectrally truncated to T42 and T106 to explore sensitivity to spectral truncation resolution. This study also focuses on cyclones lasting at least 1 day and traveling 1,000 kilometers. This study also investigates horizontal size as cyclone characteristics using our cyclone effective area detector. Cyclone size is very useful information for quantifying cyclone-related surface weather. In general, the cyclone's effective area is defined by the fixed radius of cyclones determined empirically. However, since the shape of cyclone is highly variable and complicated, defining its effective area by fixed radius could lead to misrepresentation of each actual area. To diminish this misrepresentation, we suggest a newly developed cyclone effective area detector, which consider a closed cerebral pressure control related to cyclones as cyclone effective area. This concept follows the approach of Vereny and Davis 1997. The example is shown in figure below. this detector finds a closed contour from the outermost and defined as cyclone effective area shown as shading areas. If there are primary and secondary cyclones in one closed contour, the information for detected cyclone area belongs to primary cyclone. The detected area size is measured by a cyclone effective area in this study. Prior to examining differences between sphere models and ERA5, we'll revisit Northern Hemisphere cyclone frequency at T42 and T106 in ERA5. Cyclone frequency is defined as the number of cyclones passing within the 555 kilometer radius of a grid point. ERA5 shows similar spatial distribution of cool season Northern Hemisphere cool season cyclone frequency at T42 and T106, like high oceanic cyclone frequencies over the Northern Pacific and North Atlantic, and high continental cyclone frequencies in downstream regions of the Altai Siam Mountain, the Tibetan Plateau, and the Rocky Mountains. However, there is quantitative difference between T42 and T106. In particular, the large differences are shown along the crucial glacier extension and downstream of Gulf Stream. Sensitivity of T42 cyclone frequency to atmosphere resolution in sphere models are shown in this slide. In sphere low, peaks of T42 cyclone frequency over the North Pacific and North Atlantic regions are underestimated, and cyclone frequencies in downstream regions of these high oceanic cyclone frequency regions are overestimated. The extent of bias in sphere low changes slightly in sphere medium and sphere high. The slightly better representation of cyclone frequency in the Western North Pacific and Europe is shown with higher atmosphere resolution models. However, it also shows increased bias in North America and their Western offshore area and Western Europe. Although there are some quantitative difference, it is still difficult to identify. This is sensitivity of T106 cyclone frequency to atmosphere resolution change. The T106 cyclone frequency bias in sphere low display similar distribution to with the T42 cyclone bias. However, T42 and T106 cyclone frequency biases in sphere low are changed differently to increase in atmosphere resolution. Cyclone bias over the land is still difficult to distinguish the difference between sphere models, but the bias over the ocean has a clear difference between sphere models. Specifically, increasing resolution leads to the better representation of cyclones along the main storm trend regions, but at the same time, it results in the exaggerations of T106 cyclone frequency near the downstream of regions. This different sensitivity between T42 and T106 indicates that at T106 spectral resolution, the impact of increasing resolution on cyclones is much stronger than that at T42 spectral resolution. And oceanic cyclones are more sensitive to atmospheric resolution change than continental cyclones. To understand characteristics of highly sensitive oceanic cyclones to atmospheric resolution change, distributions of maximum intensity, lifetime, and effective radius are investigated. This slide shows distribution of maximum intensity of cyclones over the North Pacific and North Atlantic in R5 and SPIR models. As shown in previous slide, for cyclone numbers, T42 cyclones show a little change between SPIR models. Both SPIR models and T106 cyclone exhibit a noticeable change. The distribution of SPIR models at T42 mostly overlap with little change in cyclone numbers. However, T106 oceanic cyclones increase with increasing atmosphere resolution through all maximum intensity. Specifically, as seen in better representation of mean values of maximum intensity in high resolution SPIR models, strongly intensified cyclone number is improved in high resolution SPIR models. However, it is noticeable that weakly and moderately intensified cyclone number is exaggerated. It indicates that, as known well, high resolution models improve extreme cyclones representation, but at the same time, we need to know that they could affect weak and moderate cyclone numbers. Indeed, it implies that increasing resolution influence the cyclone number regardless of their maximum intensities. For lifetime, we can also confirm that T42 cyclones show little change between SPIR models, but T106 cyclones display noticeable change. In SPIR law, cyclones exhibit longer mean lifetimes compared to R5, with underestimation of short-lived cyclones and overestimation of long-lived cyclones. Notably, this representation is improved in SPIR medium and SPIR high, with more short-lived cyclones and slightly less long-lived cyclones. Although this increase in short-lived cyclones lead to exaggeration of short-lived cyclone number in high resolution models. It is clearly shown in better representation of mean lifetime in SPIR medium and SPIR high. When it comes to cyclone effective radius, only T106 cyclone shows clear change with increasing atmosphere resolution with strong size-dependent signal for cyclone number change. Specifically, large size cyclone number doesn't change much, but small size cyclone number increase largely with increasing resolution. Due to this strong increment of small size cyclones, the mean effective radius for T106 cyclones is getting lesser with increasing resolution compared to R5. For T42 cyclones, mean value and their numbers do not change much. These results are consistent with cyclone frequencies different sensitivity at T42 and T106 and highly increased T106 oceanic cyclones. This finding suggested that the sensitivity of T106 cyclone frequency to atmospheric resolution change may depend on their size. The impact of atmospheric resolution change on T106 cyclones is examined with a focus on size-dependent difference. Large and small size T106 cyclones are distinguished based on a maximum effective radius of 1,000 kilometers. Shading means in this figure, shading means cyclone frequency bias and large and small size cyclone frequency bias, and contour shows ERA 5's climatic cyclone frequency. Spear low shows that a large size cyclone frequency is mostly underestimated along the peak of large size cyclone frequency in ERA 5. And small size cyclone frequency is mostly overestimated downstream of the main cyclone frequencies in ERA 5. However, it is difficult to identify difference in large size cyclone frequency bias between spear models. Only small size cyclone frequency bias exhibits the high sensitivity to atmosphere resolution change with an increase in cyclone frequency southern part of high small size cyclone frequency region in ERA 5. This strong size-dependent sensitivity is also confirmed in detected cyclone number in this table. The table shows each model and ERA 5's the detected cyclone numbers and their standard deviation. So only T106 small size cyclone numbers are significantly different between spear models. This results supports a significance of small size cyclones sensitivity to atmosphere resolution change. This study aims to clarify the sensitivity of Northern Hemisphere cool season cyclones to atmosphere resolution change in GFDL spear models. The cyclone sensitivity is clearly shown in only T106 cyclones. Specifically, increasing resolution leads to better representation in some parts, but also exaggeration of T106 cyclone number. And we can also find it results from increase in small size cyclones with increasing resolution. These small size cyclones high sensitivity underscores the importance of considering high resolution of spectral truncation in Lagrangian cyclone study. Indeed, the results implies that simply increasing atmosphere resolution does not guarantee an improvement in cyclone representation in coupled GCM. Since these increased cyclones have mostly small size cyclones, which are generally shallow, which have generally shallow structure. The cyclones, the diabatic process, which is important for shallow cyclogenesis and development, could be a key for better cyclone representation in high resolution model. Additionally, the increase in these small size cyclones could contribute to increase in precipitation in high resolution model. We are examining the relationship between the cyclone and precipitation bias now. This is all I bring today. Thank you for attention.
Oh, thank you, Jaeyeon. Yeah, I allow him to have a presentation up to 30 minutes because second presentation is not allowed today due to his personal emergency. So yeah, great. So it was well delivered. And if any questions from the audience, please feel free to let us know. And also the discussion document posted in the chat box, where you can post any questions or comments. One, two, three. Okay, I have a quick question. So, because I'm not atmospheric science major, so maybe this could be relevant for the interdisciplinary audience. So, what are the sphere LO and MED and high? The definition of them?
Sorry,
Sphere LO, low, and sphere MED, MED, and sphere high. I believe it's related. Yeah. Mm-hmm.
Oh yeah, it is. The name is related to their the atmosphere and land resolutions. So yeah, so it is just shows indicates the relatively low resolution sphere model and relatively high resolution sphere model. So yeah,
I see. Okay, 100 kilometer and 50 kilometer and 25 kilometer. Okay, so to show the scale dependency. Okay. Also, I think it would be interesting to see, because you are investigating in the higher latitudes, so it doesn't matter with the, for example, the California side or in the Eastern Atlantic, but I would want to see, I believe in the Northern hemisphere, or Eastern continental side and Western continental side, their tropical cyclone, the characteristics are completely different. So it would be beneficial to evaluate the scale dependency in the eastern side and western side. I believe your figures illustrate the effect, but you can elaborate or demonstrate or explain in the eastern and western side of tropical cyclone.
Yeah. Okay. Actually, this is for the more mid-latitude cyclones, but yeah, it could be very interesting point for studying for separately into the western parts or eastern parts, because as you can see, this figure, the overestimation is generally overestimation of cyclone frequency is generally affect to the western part of the continent, like the western North America and Western Europe.
Mm-hmm.
So yeah, it will be very interesting if I analyze the relationship between this overestimated cyclone frequency and the precipitation bias. Yeah.
Yeah, I think it would be interesting to see like ocean circulation because eastern United States and western United States ocean circulation patterns are completely opposite. So it would be interesting to evaluate those factors to impacted by the size distribution, I believe. And another question is, so can you review the tracking also algorithm used? And are these results sensitive to different methods of ETC identification? I believe more like
sorry.
Yeah. So in the chat in the discussion box, someone posed a question. So can you review the tracking algorithm used? Maybe the person who wrote the question can rephrase or Matthew, Matt.
Okay. So the question is, am I checked my results in different tracking algorithm? I think, yeah, I didn't. I haven't checked yet, but I think actually this kind of Lagrangian cyclone study is quite sensitive to the selection of the tracking method, but it is generally but generally the results are qualitatively results showed qualitatively same results, similar results. So yeah, it would be very great to test our results in the different tracking method. Yeah.
Sure. Again, this monthly webinar, week 3 for S2S monthly webinar is aimed at representing the ongoing research. So it's not yet done. So it would be beneficial to have the comments and questions to be reviewed by the author, and then those can be represented in the following studies, which we are anticipating. Okay. Any other questions from the audience? Great. Yeah, a sincere thank you to the esteemed speaker, Dr. Jaeyeon Lee, today for his valuable insights. And remember, speaker will contribute to engage with the discussion document post-webinar, so please feel free to add your questions and comments for further disclosure. Both the presentation and recording will be archived on the NOAA Week 3 for S2S website, which is also posted in the chat box. So please please put any questions or comments in the chat box where Dr. Jaeyeon Lee can contribute to it, and then which can benefit for his further study with his colleagues in GFDL and also Stony Brook University. Okay, if you have any further question, if you have any further question, let's finish our monthly webinar. So let's meet again on June 3rd at 2 p.m. EDT. Thank you very much.
Thank you.
Bye.